Hello everyone, and welcome to this webinar entitled Identifying Swallowing Function and Pathophysiology from Videofluoroscopy for Treatment Planning. This is a recording of a session that we delivered at the ASHA convention in November 2019 in Orlando. My name is Katrina Steele and I will be leading the session. I'm very pleased to be presenting along with three speech-language pathologists from my lab, Sana Smaoui, Emily Barrett, and Talia Walkin. To begin, we do have some disclosures that are listed here on the slide, and I want to point out that during this session we will be talking about a research method for videofluoroscopy analysis that was developed in my lab, which is known as the ASPEKT method, and also we'll be talking about its clinical version, the ASPEKT-C method. We'd like to take just a moment to acknowledge all of the other members of our fabulous team at the Steele Swallowing Lab at the Toronto Rehabilitation Institute. These people have all contributed to the work that we will be sharing in this webinar. In particular, we want to highlight our fabulous lab manager and engineer, Melanie Pelado-Pigeon, without whose work this webinar would quite simply not be possible. On this slide, you can see a list of the things we wanted to cover when we first wrote our submission to the ASHA convention. However, that was a plan for a 2-hour session, and the convention committee only provided us with 1 hour. So the revised plan is as follows. I'm going to begin by introducing you to the ASPEKT-C method and explaining why and how it was developed. Talia and Sana are then going to follow by walking you through the method with examples of impaired swallowing safety and impaired swallowing efficiency. And Emily will then wrap up with some closing thoughts and discussion. There are some handouts for this session as shown on this slide. These are resources that we hope will be helpful for you in your practice. In order to get the most out of this session, it will be useful for you to go to our lab website and to print the ASPEKT-C method worksheet and scoring sheet so that you have them handy during the webinar. In addition to these 3 handouts, if you want more information about the ASPEKT-C method after the session, you can access lots of additional resources on our lab website at www.steeleswallowinglab.ca in the Best Practice Videofluoroscopy Analysis section. So with that brief introduction, let's get started. Videofluoroscopy, as we all know, is intended to be a standard instrumental examination that enables us to identify impairment, determine the safety and efficiency of oral intake, to explore the effectiveness of selected interventions, and to identify candidacy for other interventions. Over the years since the procedure was introduced by Dr. Logeman, a truly huge number of parameters have been described in the literature, and a selection, but certainly not the entire list, is shown on this screen. This list is clearly overwhelming, and it leaves clinicians wondering which of these measures are really necessary to report, and which ones are the most useful. In thinking about this challenge, we have found it helpful to try to organize the various possible measures of swallowing into categories according to the World Health Organization's International Classification of Functioning, Disability, and Health. According to that framework, impairments are defined as problems in physiological functions or body structures that lead to activity limitations, that is, difficulties in executing particular tasks. And these impairments may also lead to participation restrictions. When we apply the concepts in that framework to videofluoroscopy, we think of our primary goal as being the identification of differences or impairments in physiology that help us to understand why there are activity limitations in the form of difficulties executing 2 key functions, namely airway protection and bolus clearance. We're going to use the terms swallowing safety and swallowing efficiency to refer to these key functions throughout the presentation. So in order for us to accurately identify impaired physiology that explains why a patient may have difficulties with swallowing safety or efficiency, first we need to have a really clear understanding of healthy swallowing physiology. Establishing a clear understanding of what healthy swallowing looks like on videofluoroscopy has been a focus of the research in my lab for the last few years. In order to explore this question, we first adopted a standard protocol for collecting videofluoroscopic swallowing data in healthy adults, and we began with adults under the age of 60. And then we developed and used a standard operating procedure for rating those videofluoroscopies, and we called that the ASPEKT method, which stands for the Analysis of Swallowing Physiology, Events, Kinematics, and Timing. In April of 2019, we were able to share the results of that research in this first manuscript published in the Journal of Speech-Language Hearing Research, which provides reference values for healthy swallowing for thin liquids and also for thickened liquids ranging from slightly thick through to extremely thick, according to the International Dysphagia Diet Standardization Initiative, or IDSI. In designing our standard protocol, we first made a number of choices that are shown here on the slide. It's important to emphasize that the reference values in the article and also the ones on the handouts for this session were collected using this protocol, and they may not be generalizable to other contexts. For example, we decided to use a non-cued swallow paradigm, and it's likely that some of the timing measures that came out of this study therefore cannot be generalized to the context of cued swallows. We called the standard operating procedure that we developed for videofluoroscopy rating the ASPEKT method, that is, the Analysis of Swallowing Physiology, Events, Kinematics, and Timing. The ASPEKT method is a research method that required us first to establish very clear and unambiguous operational definitions for the various events and parameters that we would identify from the videofluoroscopy. Once the events were identified, the method then involves quantified measurements rather than visuo-perceptual judgments wherever possible. As part of the research protocol, all of our ratings were made in duplicate by 2 trained raters who were blinded to each other's ratings, and then whenever there were disagreements, those cases were flagged and taken to a consensus meeting for discussion and discrepancy resolution. Before we go further, I want to take just a moment to discuss what we mean by the word normal in the context of videofluoroscopy rating. Deciding whether a patient's values for a particular measure fall within or outside normal limits is actually a very common task in clinical medicine, and a familiar example is shown here in a typical lab values report for blood testing that you might see in your patient's chart. When you look at a lab values report, it is common to see the patient's individual results in one column and to see a reference values column beside it, which enables the clinician to see how these values compare. Some reporting systems will also flag results that fall outside the expected or normal range, or they might provide qualitative interpretations such as low, or perhaps low normal if the value is approaching a boundary. In a lab values report, the reference range that is shown is usually defined as a range falling within 2 standard deviations from the mean value for that parameter, such as the range shown by the blue shaded area on this curve. And this is the definition of normal that we will be using throughout this presentation. However, although that seems fairly straightforward, Unfortunately, some of the parameters that we are interested in measuring from videofluoroscopy turn out not to have nice bell-shaped normal distributions. A good example of this would be residue, where the most common value we might see would be a value of 0, or perhaps a very small value at the left-hand end of the distribution, suggesting that there is no residue or minimal residue. And this trend gives the distribution what we call a positive skew. So for these positively skewed parameters, we will define the normal range as values that fall beneath the 95th percentile of the distribution, as shown in the blue shaded area on this curve, and abnormal values would be those that fall above that line in the top 5% of the distribution. On your ASPEKT-C reference values handout, you can find this table which shows you the boundaries that define the normal range for the various parameters that we're going to talk about in today's presentation. Notice that there are different cutoff values defining the boundaries of normal for each consistency tested. This slide shows you an overview of the full ASPEKT method that we used to establish normal reference values and ranges for healthy swallowing. And as you can see, there are a lot of steps here, really far too many to measure in day-to-day clinical rating of videofluoroscopy. On this slide, you can see a list of the various parameters that we were able to extract after performing the full ASPEKT method to rate videofluoroscopies in our research. Definitions and descriptive statistics for all of those parameters are provided in the article, starting with the values that we found for natural sips of thin liquid, and then providing similar data for the slightly, mildly, moderately, and extremely thick consistencies. Please note that the tables in the manuscript largely report this information in the form of means, standard deviations, and 95% confidence intervals for those mean values. We have now also provided an additional supplementary page of information on our website containing percentile values for those skewed parameters, and those include the median, and then the 5th, 25th, 75th, and 95th percentile values. The article contains reference values for healthy swallowing in adults under the age of 60, but we're also exploring these same parameters in a variety of other populations, beginning with healthy adults over the age of 60, and several clinical data sets as shown here on the slide. By collecting these data in these groups, we are able to pinpoint key parameters that are able to explain or discriminate dysfunction in swallowing safety and efficiency. I should highlight that our work so far has been limited to studying IDSI levels 0, that is thin, to 4, that is extremely thick liquids or pureed foods. The reference data for these levels are contained in your handouts, and it will remain for future work to look at the thicker consistencies going up the food side of the IDSI framework. So based on this research, what we want to share with you today are our recommendations for the key things that you as clinicians should measure in order to understand the pathophysiology of dysphagia in your patients. And we call this abbreviated method ASPEKT-C, or ASPEKT for use in clinical practice. The good news is that ASPEKT-C is much shorter than the full ASPEKT method. In fact, we've been able to focus in on 8 key questions that you can ask to understand your patient's swallowing. To help you explore these 8 issues, we have developed the ASPEKT-C Method Worksheet Handout. If you're going to use this method in your practice, the other things you will need are a videofluoroscopic swallow study recording, and some sort of software for viewing that recording that allows you to advance the video frame by frame, and also to make point, line, or area measurements on selected images. In our lab, we use ImageJ software for this. It's a free software downloadable from the NIH. But we are aware that there are also other softwares that are commercially available that perform these similar functions. Before we move on to some examples, I will just take a moment to orient you to the ASPEKT-C Method worksheet. The font on the slide will be small, but hopefully you have printed the worksheet and can follow along with your hard copy. You will see that the worksheet is organized into 3 sections, beginning with a section on the left called Bolus Information. Here you can record details of each bolus that you are analyzing in terms of its IDSI level and whether it is the first, second, or third bolus of that consistency that you are rating. Today, in the interests of time, we will only be able to cover examples of thin liquid. However, the reference tables on the worksheet also provide information about the other IDSI liquid levels. In column 1B, we ask you to document the number of swallows that the patient has performed for that bolus. In cases where a patient performs more than 1 swallow for a bolus, the measures in the remaining columns of the worksheet will be taken on the first or initial swallow. However, there will be places where you also document observations of change on subsequent swallows. I'm now going to hand over to Talia, who will take us through some examples involving impaired swallowing safety.
One of the main parameters assessed by videofluoroscopy is airway protection, including the evaluation of the potential for and the cause of penetration and/or aspiration. On the ASPEKT-C handout, you will follow along in Section 2, Swallowing Safety. Here, the main areas of focus will be on the penetration-aspiration scale score and its possible evolution across swallows, as well as the laryngeal vestibule closure, integrity, and timing. Over the next set of slides, I will walk you through each of these definitions, as well as provide case examples that will hopefully help you understand how this can be applicable for your own patients. Let's start by looking at the 8-point penetration aspiration scale that has become the standard way of describing the severity of aspiration. The scale can be broken down into different levels. At the top, the first 2 rows describe material that does not enter the airway at all, or that briefly enters the airway, but is then cleared. These levels are seen in healthy swallowing. In 2018, Steele and Grace Martin slightly adapted the scale to include what was known as Level 4 in the top level of the scale. Level 4 describes material that contacts the vocal folds but is ejected from the airway. In ASPEKT-C, scores of 1, 2, and 4 are considered within normal limits, as no material is left within the airway. Scores of 3 and 5 describe material entering the supraglottic space and traveling as far down as the vocal folds, but not below, and that is not ejected. The scores of 6 to 8 describe material falling below the true vocal folds, whether ejected or not. Under this section, we will only be looking at the first swallow of the bolus. We will take a closer look at the evolution of pass across swallows, or 2E, later on in this section. For our clinical purposes, scores of 1, 2, and 4 are considered as being within normal limit, and you would skip to Section 3 of ASPEKT-C Method to review swallowing efficiency. But scores of 3, 5, and higher fall into the impaired range. In reality, whenever material enters the supraglottic space and stays there, it is at risk for eventual aspiration. With scores of 3, 5, and higher, we would move directly to 2B, laryngeal vestibule closure integrity. Laryngeal vestibule closure, or LVC, is one of the most critical parameters to look at when determining whether or not a patient is protecting their airway. Abnormalities can occur both in timing and the degree of closure, but we will start by looking at degree of closure. To do this, you need to find the frame of maximum LVC. That is, the frame when the arytenoids rise and contact the undersurface of the epiglottis. The question is whether or not the contact is complete or leaves a gap open through which a bolus can be penetrated or aspirated. Based on prior work in our lab, the odds increased to 22 times the risk of penetration aspiration scores of 3 or higher when incomplete LVC was observed on an initial swallow. So, when completing the ASPEKT-C form, if LVC is complete, we will move on to 2C, pass timing. However, if LVC is incomplete or absent, please move directly to 2E, pass evolution, and then to 3.0, swallowing efficiency. We do this since we have just identified that incomplete or absent LVC is likely the mechanism of impairment and should be targeted for treatment. Once we have established that material has entered the patient's airway, we need to start asking why. For this, we want to take a closer look at when LVC is happening. There are 2 scenarios in which LVC can be complete where you might still see an impaired pass event. This happens when the pass event occurs prior to LVC, or when the pass event occurs after the laryngeal vestibule has begun to open after its full closure. In each case, we would take a different course of action. In 2C of the ASPEKT-C method, we just want to establish if the pass event is occurring before or after LVC. For now, we're going to focus on what to do if pass occurs before LVC. When the pass event occurs before LVC, the assumption is that the system may not have reacted quickly enough to the incoming bolus. This is clinically relevant as your patient may have a delay between the time from their hyoid burst, which we define as the first anterior superior jump of the hyoid that is associated with the swallow, to LVC. If a delay in closure occurs, this provides time where the bolus can enter your patient's airway and contribute to a pass event. In ASPEKT-C, we call this measurement time to LVC. However, from previous literature, you may be familiar with this measure being referred to as laryngeal vestibule reaction time, or LVC-RT. I am going to take a quick detour before I discuss pass after LVC and pass evolution to walk you through a case example. For the sake of time, I'm going to provide you with the ASPEKT-C results. What we can see from this video is that the patient has a pass score of 8. Material has passed below the true vocal folds and there is no response from the patient. LVC is complete. Pass has occurred before LVC. And because the pass occurred before LVC, we move to 2D. Here we want to calculate the time to LVC. In this case, the time to LVC was 20 frames. The hyoid burst frame occurred at frame 1468, with the laryngeal vestibule closure occurring at frame 1488. The difference between the 2 measures was 20 frames. 2E, or pass evolution, which we will discuss in our next case example, would be marked as not applicable because in this example, the patient swallowed the bolus in 1 swallow attempt. Now that we have all the measures required to compare our patient swallowing safety to healthy swallowing norms, we are ready to move the values to the next part of the worksheet for this comparison. Using the ASPEKT-C reference values, we can determine whether our patient's measurements are within normal limits for each consistency. For this case, the pass score of 8 is impaired as compared to 1, 2, and 4 in our reference value chart. The LVC is within normal limits since it was complete. However, the time to LVC is impaired. With time to LVC, we must convert our 20 frames into milliseconds. To do this, I took our 20 frames divided by 30 frames per second. That equals 0.66. I multiplied that by 1,000 to convert to milliseconds. That equals 667 milliseconds, which is greater than 379, as seen in our reference values. This would lead a clinician to identify time to LVC as being the mechanism of impairment for swallowing safety and a target for your treatment protocol. So let's take one final jump back and ask, what happens when the pass event occurs after LVC? Our original assumption here was that this might be explained by LVC duration, or the length of time that the laryngeal vestibule is closed. We assumed that the laryngeal vestibule must not be closed for long enough, therefore allowing penetration or aspiration to occur before the bolus had time to pass through the pharynx. However, after exploring different populations of patients that we have seen in our lab, our data did not show that LVC duration contributed to a pass event occurring after LVC. Therefore, we suggest that if you are seeing a pass event in your patients after LVC, to consider if the patient's swallowing efficiency may be contributing to the pass event. In relation to the ASPEKT-C method, you would bypass 2D and move to complete pass evolution, which is the final parameter we will talk about in this section. Because in ASPEKT-C, we are only referencing the initial swallow on the measures described so far, we think that it is clinically relevant to capture any evolution of pass. As seen in the example here, if your patient has a pass of 3 on their initial swallow, and then continues to swallow in attempts to clear the bolus or any remaining residue, and pass evolves to a 7, this would be noted in the pass evolution column of the ASPEKT-C method. Now, let's take one final look at this video in reference to the ASPEKT-C method. LVC is complete, pass occurs after LVC, and LVC timing would be marked as NA, since the pass event occurred after LVC. Now that we have all of the measures required to compare our patient's swallowing safety to healthy swallowing norms, we are ready to move those values to the next part of the worksheet for comparison. When we compare the reference values to this case example, we see that the pass score is impaired. This is because the chart is to be completed with only the worst parameter values per consistency in order to fully capture impairment for that bolus consistency. So instead of capturing 3 for the initial swallow, pass will be marked as a 7. The LVC is within normal limits since it is still complete, and because the pass event occurs after LVC, we would not complete 2D in this section. And as mentioned, this would lead a clinician to question whether swallowing efficiency is impacting swallowing safety, which Sana will now take you through.
A second criterion that needs to be considered when determining whether your patient has a swallowing impairment is swallowing efficiency. Efficiency is defined as the ability to clear material through the pharynx. As we can see in this image, this swallow is inefficient, and there's a significant amount of residue collecting in the vallecular, piriform sinus, and other areas outside of these pockets. You will notice that your ASPEKT-C handout contains the swallowing efficiency section, which we'll be focusing on over the next set of slides. Using the ASPEKT-C method, we've narrowed down 3 measures to denote swallowing efficiency. 1. Total number of swallows per bolus. This is the number of swallows taken to clear 1 sip of liquid. 2. Pharyngeal residue. This captures the amount of residual material in the pharynx. And lastly, 3. We consider pharyngeal area at maximum pharyngeal constriction, as this parameter correlates with post-swallow residue. In order to measure pharyngeal residue and pharyngeal area at maximum pharyngeal constriction, it is important to scale these measurements to the cervical spine of the individual on the selected frame of measurement. This is crucial, as eyeballing residue is susceptible to differences in pharyngeal sizes. Scaling our measurements to the length of the C2-C4 cervical spine from the anterior-inferior corner of C2 to that of C4 controls for differences in the size of the system, including sex-based or height-based differences. More importantly, using this method, one is able to extract a measure for residue while controlling for other variables and tailoring measurements to the individual's anatomy, allowing for comparisons to be made between anatomically normalized measures within a patient at different time points or across patients. Pharyngeal residue is a term used to describe material remaining in the pharynx at the end of a swallow. In order to measure pharyngeal residue, one must select the frame in which the swallow appears rested. The swallow rest frame is the first frame showing piriform sinuses at the lowest position prior to the introduction of new material. Our first question to consider is whether we see any pharyngeal residue at the end of the initial swallow of the bolus. If no residue is seen, then there is no need to complete any pixel-based area measurements on the ASPEKT-C worksheet, as swallowing efficiency is not impaired. If the answer is yes, then measurement is required to determine whether the amount of residue is outside normal limits. A pixel-based tracing of the area of residue is indicated here for 3 locations of residue: follicular, piriform, and other residue anywhere else in the pharynx. These numbers, along with the cervical spine measurement at the frame selected, are used to calculate overall pharyngeal residue. For this case, we have counted the total number of swallows to clear a trial of ITSE level 0 thin liquid by cup sip. This patient used 3 swallows in an attempt to clear residue. We identified the frame of swallow rest after the first swallow, and as can be seen here, noted post-swallow residue. Residue for each area was measured using the area tracing function in image J, and the number of pixels for each residue area tracing was noted. Next, we measured the length of the C2, C4 cervical spine so that the squared reference area could be calculated. A quick note about residue. Residue should only be traced after the initial swallow when comparing to norms. Thus, an increase or reduction of residue following subsequent swallows on the same bolus should not be captured under this heading. The formula for calculating total residue is listed here. Simply add all 3 areas of residue and divide them by the squared value of the C2-C4 length. We multiply the value by 100% in order to determine the area of residue based on the C2-C4 scalar. Next, as residue was identified, we need to consider pharyngeal area and maximum pharyngeal constriction. As cited in the literature by Stokely and colleagues in 2015 and Waito and colleagues in 2018, reduced pharyngeal constriction is significantly related to the presence of follicular and piriform sinus residue, as well as the number of swallows taken per bolus. In order to measure this parameter, we need to select the frame in which the pharynx is in its most constricted state during the swallow. Once this frame is selected, we can measure the area of visible airspace or bolus above the upper esophageal sphincter and below the top of C2 to obtain a quantitative value. Now let's apply these measures. First, we determine the frame of maximum pharyngeal constriction as seen in this image. We then trace the remaining unobliterated area of bolus and airspace. You can see the traced area highlighted in yellow, bound by the green line at the top of C2. The C2-C4 cervical spine length is also traced and highlighted in red. These values are inputted into the formula to calculate the pharyngeal area at maximum pharyngeal constriction, which for this case is 14.7%. Now that we have all the measures required to compare our patient's swallow efficiency to healthy swallowing norms, we are ready to move the values to the next part of the worksheet for this comparison. Using the ASPEKT-C reference values, we can determine whether our quantitative measures are within normal limits for each consistency. For this case, we had used an ITSE level 0 thin liquid consistency. We can see that healthy normal reference values for number of swallows is 1 to 2 swallows, which would indicate impairment for our patient who took 3 swallows. Normal reference values for total pharyngeal residue fall below 3%. This means that our case with a total pharyngeal residue of 20.1% falls outside normal limits and interpret this parameter as impaired. And lastly, we consider our measurement for pharyngeal area and maximum pharyngeal constriction, which is greater than the normal reference value of 4%. Here, we also interpret our pharyngeal area and maximum pharyngeal constriction value of 14.7% as impaired. As only one bolus was used in the previous safety and efficiency examples, the values for that bolus were the ones used to compare against normal reference values. We recognize that an SLP will trial more than just one sip of a particular bolus consistency on videofluoroscopy. When more than one sip is trialed, all trials are to be measured according to the instructions on the first page of the worksheet. However, the My Patient Values chart is to be completed with only the worst parameter values per consistency in order to fully capture impairment for that bolus consistency. Additionally, we note that the frequency at which an impairment occurs is not captured here. If a particular parameter did not show impairment on all trials, it may be salient to capture this in the text of your report. As only one bolus was used in the previous safety and efficiency examples, the values for that bolus were the ones used to compare against normal reference values. We recognize that an SLP will trial more than just one sip of a particular bolus consistency on videofluoroscopy. When more than one sip is trialed, all trials are to be measured according to the instructions on the first page of the worksheet. However, the My Values chart is to be completed with only the worst parameter values per consistency in order to fully capture impairment for that bolus consistency. Additionally, we note that the frequency at which an impairment occurs is not captured here. If a particular parameter did not show impairment on all trials, it may be salient to capture this in the text of your report. Performance is not collapsed across consistencies using the ASPEKT-C method. Therefore, reference values are provided for all ITSE levels along the liquid side. As mentioned during the examples, we identify the ITSE level associated with our measurements when comparing these to normal reference values, as the reference values are unique to each consistency.
So it's important to acknowledge that we presented a lot of dense information, and that none of the speakers on this recording learned the ASPEKT-C method in 20 minutes based on one example of each parameter. Just like none of us listeners learned to analyze videofluoroscopies in any of the current ways we do them based on one single example. As Professor Steele mentioned at the beginning, this information was never meant to be presented in 40 minutes, so if you walk away from this recording feeling overwhelmed or like it was a lot to digest, it's a perfectly normal response. The question now is, how do we conclude the presentation and have something stick? And instead of presenting another swallow clip, we wanted to spend the last few minutes talking about the why of the ASPEKT-C method. Why we want to inspire you to go back to these notes, discuss and debate these ideas with your teams, and then consider the why of the quantitative method we're proposing we start to use as clinicians. So far, we've spoken to you about the what, that ASPEKT-C is a quantitative norm measure of videofluoroscopy analysis. And we've talked about the how, demonstrating how to use it with a few examples looking at swallowing safety and swallowing efficiency. But I want you to put all of that aside for a minute, because what anyone will tell you is it's the why of the method that will drive change and evolution in your practice. And the why of ASPEKT-C is this. We believe we can continue to do better in the analysis of videofluoroscopies. We've made huge gains in the field, with there being a growing awareness and acceptance of the need for a standardization of tasks and definitions across clinicians and institutions. But it has been recently said that we can continue to do even better. A great example of this is the Katina Swan et al. Article that came out in Dysphagia in 2018, which made reference to the fact that the majority of our current fees and videofluoroscopy analysis measures psychometric properties were indeterminate. So our lab has been looking for ways to improve video analysis. And this starts with us questioning, what is the best kind of scaler to measure swallowing? Ordinal scales that currently exist for swallowing analysis work like buckets. An example would be using a scale that had a bucket for 1 mild, 2 moderate, and 3 severe. And based on what we're continuing to learn in swallowing research, we wonder, is an ordinal scale still exclusively the best method? Or are we missing critical changes between these buckets? Is there a 0.5 bucket that's relevant to my patient or a specific population of patients? Do ordinal scales adequately capture timing, something that is so critical to pass in swallowing safety as we discussed? And lastly, but most importantly, are the visual perceptual judgments that I'm using to put something into one of these buckets always accurate? We looked at that last question internally in our own lab. As a lab that does ratings of literally thousands of video swallow clips after extensive internal training with duplication and regular consensus meetings, we thought, hey, we should be pretty good. We used the Eisenhuber scale, an ordinal residue rating tool, which puts, when we see it, residue into one of 3 buckets listed here on the slide. These are pretty generously sized buckets. We rated these buckets on 3,545 boluses from 305 patients, and then afterwards quantitatively traced and compared the two. This graph looks at our tracings of molecular residue. Bottom line, our visual perceptual judgments weren't so accurate. The truth is, this graph shows that we incorrectly underestimate with small amounts of residue, both under and overestimate when residue amounts fall in the middle, and then move to exclusively overestimate residue with larger amounts, even within these generously sized ordinal buckets. And you might say, well, the vallecula is a small space, and the epiglottis can sometimes be collapsed, further confounding our judgments. I wonder about the piriform sinuses. Would our judgments there be any better? And honestly, piriform sinus judgments were not much better, and we see the same trend, though not as pronounced, with the underestimation of small amounts of residue and the overestimation of larger amounts of residue. With all of this in mind, ASPEKT-C method moves towards quantitative scales like the measuring tape on the right. This allows us to do things like capture swallowing timing in milliseconds, and capture swallowing efficiency as a percentage of your individual patient's C2-4 space to tailor risk assessment. It should be noted here that while our lab has found that based on the research, these 8 parameters are often the ones that tell the mechanism story, ASPEKT-C can also serve as a starting place for videofluoroscopy analysis. You may wish to follow an ASPEKT-C analysis with another videofluoroscopy tool that adds other descriptors to your patient's profile. This may mean that in your report, you include a combination of measures, including our proposed quantitative measures, as well as some qualitative ordinal scale data, such as the MBS-IMP. So, to summarize what we've covered to date, the why of the ASPEKT-C would be 1. Because it's a clinically geared quantitative measure of videofluoroscopy. It measures swallowing timing in milliseconds and swallowing efficiency as a percentage of your patient's C2-4 space. 2. Because ASPEKT-C is normed on healthy swallowing reference values, grounding our clinical decision-making. 3. Because all of this information then leads us as clinicians to clearer guidance on the mechanisms of impairment, which is so crucial to creating a solid foundation to treat dysphagia accurately, as Professor Steele mentioned at the beginning. While ASPEKT-C's analysis may be slightly longer to start than your current process, it can save us time as clinicians on the treatment back end because we know we're specifically targeting the right parameter of interest. And 4, because like we mentioned in the swallowing efficiency section, it's clinically relevant to understand how patient performance differs across consistencies, as opposed to collapsing a patient performance in a way that doesn't distinguish. For instance, we know from healthy norms that time to laryngeal vestibule closure differs across consistencies. So this may be an issue with thin, but not extremely thick, and that's relevant to the recommendations we make for our patients. So if you're still thinking, well, maybe this method is only something researchers should do, consider the slide that Professor Steele showed you at the beginning of the presentation, listing all of these video parameters that exist in the literature. And this is not an exhaustive list. Those were then boiled down to the ASPEKT research method shown here. We scored the whole thing on healthy volunteers as well as patients with dysphagia to figure out what was clinically relevant so that you as a clinician don't have to complete an exhaustive list of measures. This led to a simplified version, the ASPEKT clinical or ASPEKT-C method we've been talking to you about today, that focuses on these 8 parameters that tell the mechanism story most often. Why is it important for the ASPEKT research and ASPEKT clinical methods to be based on one another? It's important because clinicians and researchers need to begin to speak more of the same language, use the same terminology, and take the same measures. For us as clinicians, it makes it easier and more straightforward to consume, interpret, and implement research in our own practice because we're talking about the same things. And actually, this theme of the research translation problem was covered in an article in the ASHA Leader in July 2019, and if you're looking for some interesting reading, I suggest it. Its recommendations on how we can bridge the clinician-scientist gap across many speech and language-related fields, not just dysphagia, are something we've recently tried to keep in mind when working in our own lab. Okay, so where do we go from here after you're done listening to this recording? Our hope is that the conversation doesn't stop here. Consider bringing these ideas back to your teams. Talk about the ASPEKT-C method with colleagues, or share it in a journal club or SLP discipline meeting. Go back to what we just talked about and lead with the why. Why is always at the gut of what feels clinically right. If we don't talk about the why first, the what and the how don't matter. You're not going to remember everything we talked about in this recording. Go to our lab's website, download the instruction sheet, read the step-by-step manual. It's all open access. Email us and ask us questions. There are no bad questions. And then try the ASPEKT-C method with a patient. Start with just one. Do it with a colleague. Honestly, like anything new, the hardest part is the start, and once you've done it once, it gets faster. Most of all, our intention is that once you try this, you'll be able to see the inherent value of taking these quantitative measures, to understand the mechanism of impairment to guide your treatment, and you'll be motivated to do it again. So a final thought to leave you with. So many of our practices in our facilities are driven by metrics, whether that's length of stay, number of meters walked, CBC lab values. Meaningfully and sensitively capturing change in our patients is so important in the world of big data. We as SLPs work so hard to accurately assess our patients' swallowing and treat it, that beginning to quantitatively capture that change may be the next step. We already do it with speech and language, for instance, when we report that a patient has moved up X standard deviations on their B&T relative to age-match healthies. Now being able to say that someone's swallowing parameters have moved to fall within normal limits relative to numbers from healthies may be helpful to better contextualize the hard work our patients already do with us on this big data, metrics-driven stage. Thank you so much for listening to this recording. If you have any questions, please take a look at the FAQ posted on our lab's website for common questions we've received about the ASPEKT-C method. We've also posted links here summarizing some of the resources we've discussed throughout the presentation. If these resources don't answer your questions, please feel free to reach out to us, either through email, at our Twitter handle, or on our Facebook page.